Hi everybody and welcome to another class. Today we're going to talk about something very unique, very special, diffusion mechanism and how it's relevant to drug delivery. But before of that, we need to cover the basics. So I want to introduce to you what's happened historically, or as the story goes. We had a botanic guy named Robert Brown. And Robert Brown was a botanical and he learned about flowers and the different species of flower. And he wanted to check the flower, and he saw something very interesting under the microscope. He saw that if he put pollens in water liquid, he saw that they start jiggling around. And this was very weird to him, and many people observed this phenomena at the past, but nobody stopped to really think about it. So he thought maybe this was because of something that's alive, so something is living there, or maybe the desk is moving or stuff like that. And he started to eliminate everything step by step. And even when you see this is the Brownian motion, random motion this pollen of the flower is doing. And when he started eliminating, he finally got, I'm going back to there, to very interesting conclusion. He took a crystal, and inside the crystal there was air and water, and he saw that in this place nothing could be alive, because for thousands of years this is isolated from the environment, and he still saw this movement. So he got a lot of credit and realized that this is not about a living thing. This is a basic fundamental physics or chemistry, or you don't know, quantum mechanics phenomena. Okay? So the story goes that after a few times, this very speculate thing, this scary movement, been investigated by many researchers. And what we're going to do, we're going to take step with the researchers, and we're going to revive what they did. For example, Louis from French wrote his PhD thesis under the name The Theory of Speculations. He put particles, I'm going to show you, and that's going to be our first question. I'm going to write everything on the board. He put particles, you see, in x equals 0, and he gave them this random movement. And he tried mathematically to understand this mechanism. Because if you're going to put a particle, it could be in your suspension in the lab, it could be inside the lungs, inside the blood as a treatment, suddenly this phenomena of diffusion going to happen. So what I want to do is to cover with you this phenomena. So let's go to the board, and I'm going to introduce to you a simplified model, and we will try mathematically to understand what is diffusion. So the model is like this. We're going to solve random motion of particles, but only in 1D. Then we're going to do the conclusion to higher dimensions. So this is the x-axis, and this is the location 0, and I'm going to distribute a lot of particles at that location. How many? In total, okay? And total independent particles here in the center, and every now and then, okay, which means every tau second. Okay, let's write first of all this one, like at t equals 0. All the particle, you see the particle number I, out of all the total, is at the location t equals 0 equals 0. Okay, so this is our initial condition. So what's going to happen with time? If we look at this random motion, some of the particles decided to jump to the left, or maybe to the right. That's what happened. So let's take this assumption. So I'm going to say that every tau seconds, there's going to be a jump. The particle I, right? Particle I, out of all of them, will jump in what distance? Delta. Yeah, let's make it general. Gonna jump delta to the left or to the right? I don't know. It could be positive or negative. For example, this particle could jump to here, to plus delta. And if you're going to wait another tau seconds, it can jump here to 2 delta. Or it can jump back to 0. And this one can jump minus delta. So just start jumping around, jiggling around, and we're going to give that each one of them, the chances for plus delta equal the chances for minus delta equal 50%. Okay, so this is another thing. And something that I want to emphasize is that the particle is independent. They don't see each other, they don't interact with each other, they don't combine, they don't break apart. Each one live in a separate world. That's going to make the assumption easier. And now I want to present to you a non-dimensional number, we can say, but something that's easier than time, okay? So if we're going to think about it, at each particle, let's do it in black. So in general, the motion of the particle, we can set the particle I at time t equal to the particle I, the same particle, in the previous time, right? The previous time plus minus delta, right? This is the location of every particle. You see it? And this is clear? One step before, add the step that I need to jump, right? So this is my current location. And I can present this as a non-dimensional number regards the time. I can, instead of presenting the time, we can talk about steps. I can use n. And what is n? N is just a simpler idea, is what jump we are talking about. The first jump, the second jump, the third jump, the fourth jump. It's like time. So the definition of it is the total time that's been passed so far divided by the time it takes to jump. Very simple context, right? So this equal to xi n minus 1, right? Plus or minus delta. Okay. So I think that would be an easier concept to understand talking about jumps. Okay? So that's the idea. And what I want to ask and what I want to raise, in general, we are interested in knowing the location of the particles due to gravity, due to diffusion, due to electrostatic, due to magnetic, where the particles going to be. What is the characteristic length they're going to move, or time they're going to deposit in that time? We want something to grasp on. You feel me? You understand what I'm talking about? So we are looking at what is the characteristic time that's going to produce to me some distance. And we don't know it, so let's find it out. So maybe the average location of the particles isn't a good idea. I'm going to look at all the particles in some random time. Let's say this time. There's some here, there's some here, there's some here, there's some here, right? And we're going to look where's the average location of everybody. Okay? So first assumption, here, maybe. Okay, I'm going here. So A, first section, this was the given data, right, of the model, is LDiff. When I write LDiff is the characteristic length due to diffusion, equal to the average. Okay, so this is a sign for average. I'm gonna, you see these two? Question mark, and I'm gonna remind us what is average. Average is taking, we can do it with smileys, I love smileys. So we're taking what is the average of all these features. For example, how happy are each particles? To know that, you need to sum all the particles, right? Sum them all and divide it by the total number. You sum the first one, I equal 1, until, and total. This is average in general, average. But we're not interested in happiness of particles, we're interested in location, okay? Okay, so I assume all the particles are happy, okay? So, again, question?
A is like
yeah, is section A, yeah. Question 1, yes, section A. Good, thanks for the clarification. So this is a friendly reminder. That's how you find average. So what is the average location of the particle, general particle I, and at time or a jump number n? General idea, okay? So we have the formula, so we're going to divide by n total, and we're going to sum all the particle locations at in, right? I, the first particle we observe until the final particle. Great. So I can just plug in the identity for the location. We know it. We can go one step before. Okay, so I'm going to use this concept. I'm going to use this concept. So we know that. So this one equal to what? Let's write it. It's equal to xi, the previous step, plus minus, give me a jump, right? Okay? So now, if I'm going to operate this on top of that, what I'm going to get? What I'm going to get, so this is equal to 1 over n, right? I'm going to do a summation of xi n minus 1 plus minus delta, right? And I'm going to get two terms. The first term going to be that 1 over n sum of xi n minus 1. So this is the first term, plus I'm going to get this term, right?
No.
Why?
Shouldn't, like, sum?
Sum, okay, sum, okay, sum. So let's think, okay, it's a good point. So let's think about it, okay? So if we're going to sum plus delta and minus delta and plus delta and minus delta and plus delta and minus delta, so this term is going to be 1, minus 1, or 0.
No.
It really depends.
It can be like even n.
Yeah, it can be many things, but in general, as bigger my n, as I approach n to infinity, the chances of that being 0 is increasing. So I'm going to take n to be a very big number, and for that, this one can be eliminated, okay? But what's really interesting is what is this value? Do you recognize what is this? 1 over n, sigma of the previous step. What we actually got here is a time machine. I don't know if you see it, but what we got here is that the average at the jump number n equal to the average of the previous jump. This means that the average does not change in time. You see it? Because every time I can take the previous step. So I want to remind you, so what was our first time, the 0 jump? All the particles were at the location, right? All the particles, so I'm going to sum 0 plus 0 plus 0 plus 0 plus 0 divided by n total, right? So we found out that the average of all the particles equal to 0, and for that reason, that was a very bad idea, okay? I'm going to the presentation, okay? So what actually we saw here, that maybe the particles started in x equal 0 at time 0, but you see how they spread around? So they spread around the 0 all the time. So the average is always 0, okay? And if you're going to check my model and you're going to try to have a probability where the particle, you get a beautiful normal distribution looking like that, okay? So we need another method to evaluate how much particle diffuse around. Okay, do you have any idea what we can use? Huh? So, great idea. So what was our problem? Problem was that all these plus and minus actually canceled each other out. Okay, that's what happened because one particle moved to that side and one particle moved to that side. And the average location of them is 0. They cancel out. So we want something square in order to understand how many particles diffuse to the right and to the left. Okay, so the best idea is to use the standard deviation, sigma. So if we have probability and this changing in time, what's happening in time? We have a lot of particles in where we put them and then they start to diffuse around and distribute and fill all the space, right? It's like having a tea bag you put inside hot water. Everything starts concentrated in one location around the tea bag, but if you're going to wait enough time, it's going to distribute it to all the cup. It's going to be the same color. So that's what's going to happen. This diffuse and spread in all space. So our next assumption is, let's check if sigma is a good characteristic length for our problem. So B, right? And now we're going to raise the question, is L diffusion we are talking about, right, can be sigma, the standard deviation. And just a friendly reminder, again, I know maybe some of you didn't do statistics for a long time. So the definition of sigma is the square of the variance, which is actually equal to the average. I need to do average. Inside the average, I do a square. Inside the square, I take the specific location of the particle I at time n, minus the average location of all the particles. You see that? And for us is even easier. Why it's easier? Because we know that for our case equals 0, right? So we actually looking L diffusion equal to sigma, which equal to the average on xi n squared, right? No, you have it inside this thing, right? It's inside the operator of doing average, okay? So we're actually looking to find this. So I see here, in general, 3 problems. We need to figure out the argument, right, to square it, and then we need to take the average, so let's call it 1, 2, and you know the square root is not a dead problem. Maybe it's going to cancel with the square, or we can look at sigma square or L diffusion square. It's not a big problem to get rid of the square, okay? So that's what we're going to try to solve. So let's look for, I'm going to go to that side of the board. I'm going to go here. Okay, so we're going to substitute everything. So let's start with our argument. Okay, so the argument of this standard deviation that we are talking about is the definition of the location of the particle square. So no problem. L diff, maybe it's sigma, right? So we're going to start with finding what is xin square, right? This is the first step. So I take this term, xi at a number jump n, which is our time, plus minus delta, we don't know it, squared. So I can open the square, no problem. So we have xi at the location n squared, plus minus, because I don't know the sign, right? 2 delta xin, and plus delta square. Okay, we found it. Good question.
N minus 1?
Huh?
Like xi
Sorry. Yes, good point. Very good point. Yes. And yes, and also here. Right? Perfect. Good idea. Okay? Great. So now what we need to take of that? The average, right? To sum everybody. So what is the average of this creature, right? So the average of this creature is to apply the operator of averaging, right? This is not a very good one. So we're going to apply the operator which said divided everybody by the total number, and please sum everything from the first particle until the last one, okay, of the term. So here we're going to write again xi n minus 1 square plus minus xi n minus 1 plus delta square, finish, right? Okay, so what we're going to get here, I actually see that we're going to have 3 terms. You see that? So what each term going to be? So the first term going to be 1 over n sigma xi n minus 1 squared, right? And if you're going to look really careful, what we got here? Again, we get a time machine. See it? What do you mean? I see an average, right? This is the idea of averaging. This is the average of the previous jump squared. You see it? So this is a time machine. Great. Let's go here. So this one, you know, 2 delta I can pull outside of the average. It's a constant, right? So 2 delta, 1 over n, sigma xi n minus 1. Okay? And plus minus. What do we see here? What is this? This is the average, right? I don't care about what time it is, because the average always is 0. So this one is canceling out. Last but not least, delta square. So if we're going to do 1 over n sigma delta squared, I'm going to end up with n delta squared divided by n. This n comes from the sigma, and this is just equal to delta squared. Right? That's what we got. Clear? Perfect. So in general, we looked that we have some time machine and a correction, delta squared. And that's exactly what I wanted. I wanted to cancel up the minus and plus and minus, right? So it's good to me that we have here squared. Good. So in general, we found out that xi squared at time or jump is the same thing, n equal to the time machine, the previous one, right? Plus delta squared. Okay, I don't know what it's equal to, but we can start to substitute different times and see where this is taking us, right? I can have the time 0, the time tau, the time 2 tau, the time 3 tau, and so on. I can have the non-dimensional time, yeah, which is a fancy name to say what jumps we have, right, which n equal to t over tau, which is the jump number 0, the first jump, the second jump, the third jump, and we can calculate this value, xi n squared, based on the formula that we have. So let's see where this is taking us, right? And this is at a general t and a general n, right? So if we're going to try to do it, so this is 0, right? So it's actually xi at the time 0 squared. So all the particle at the location 0, right? Square 0 is 0, average on 0 is 0. So the first value is 0. Not looking good, okay? Let's go another step. So the next step is xi squared at the location, you see the location n minus 1, right? N minus 1 is 0 plus delta squared. So this is 0 because of that. So the result is a single delta square. If you're going to continue, this is equal to xi squared 2, right? 1. We are looking for 2. Yeah, 1 plus delta square. This is equal to delta square plus delta square, so 2 delta square. You start to feel the pattern? If we're going to do it here, xi 2 square plus delta square, this is equal to 2 delta square plus 3 delta squared. So eventually, if we're going to continue in this pattern, the result is n delta squared. You see it? That's what we got. Our sigma, we found, and we know that L is a distance square, right? And we need to take the root of it. We are also good with units. So in general, oh, this is great. So in general, right, I can say that we found that xi squared of n is equal to n multiplied by delta square, right? And here we can write sigma square and get rid of the root, right? And we considering that to be our characteristics diffusion length, okay, squared, right? Yes. So we can also write it in even more simpler way if you're going to look at it. So if I want to present it as a function of time, what I need to do instead of n? Yeah, so the non-dimensional, it's just divided by tau, delta square. Perfect. So in general, I see this relationship. L-diff is equal squared, equal to t over tau, non-dimensional, multiplied by delta square. And I want you to see something very interesting. Delta, okay, is how much the particle can jump. Very far away or not that far away. And tau is how often the particle is jumping. Jump, 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 or jump, jump, right? So these two phenomena related to the physics of the problem. You see it? Right? Physical properties. So I can give them a name to be one constant, right? I can write L diff squared equal to T multiplied by constant D. I can do that. And D is equal to that, right? But I want to take one step farther and say 2D, okay? So this one is equal to that, okay? So maybe you're gonna ask, Ron, why you put 2? So the explanation would come in the next hour, okay? But bear with me. So this is some characteristic length that tell us how much particle would move. If I'm gonna release particle here, for example in the trachea, okay, in the trachea, and they're gonna start diffuse in time, I can approximate when they're gonna do a radius. They're gonna do this distance at that time, okay? Is that clear? Let's try to check it. Let's see if you understand it. So I have another question for us. So this is section C. Provide an approximation of the time it would take for a given bacterium to digest food. Okay, this is the question. We see here we have a scale bar of 1 micrometer, and this scale bar is approximately the size of the bacteria. The bacteria is 1D, right? The food is going along this channel, right? And it's given me the diffusion constant of the physics, and I wanted to see the units of the diffusion constant. What are the units? Meters squared versus second, right? Over second. Which means if I release something, think about tea bag is the best example for me. Tea bag, so the area that the tea bag is propagating time is an area versus second, okay? It's kind of a flux. People that know Fick's law, if you know this about diffusion, so here it's coming back. So we're doing much more basic stuff than Fick's, okay? What Fick's did, okay? So let's try to solve this question, okay? So I'm gonna clean the board. Let's clean it, okay? Perfect. So I see that the marker's working really good because I'm trying very hard to clean it. You don't see it. It's look effortless, but I'm doing a really hard job. Okay, so let's try to solve this question. Okay, so we have a bacteria. Here's the bacteria. Yeah, we can do it even scary bacteria. And it's want to digest some food particles. And when the food particles would enter the bacteria, right, they're gonna start to diffuse around through all this organ, right? And what we're interested in is what? Is how long this gonna take, okay? We know that these particles diffuse in an order of 10 to the minus 9 meter per square per second. This is a 1D problem, X, right? And we know that the length of the bacteria is approximately 1 micron based on the scale bar. If the bacteria was larger than the scale bar, maybe a few scale bars. But I can relate approximately. And remember, this is an approximation. Okay, just need to give me a feeling. It's gonna take a full day, or it's gonna take a second and we can move on. I need to wait or I don't need to wait, okay? That's a general idea. So what is the formula? We have it over there. Very easy formula. So the formula that we did is the diffusion distance square equal to 2 times this constant d multiplied by the time that passed by, okay? So I just gonna find t. T is equal to L diffusion squared divided by 2d equal to 0.9, 10 to the minus 9, 10 to the minus 6, the length of the bacteria squared, and this is half of a millisecond. Very fast, okay? Very fast, okay? Why did we study this? Why did we study this diffusion? This is clear? Sorry, multiply by 2. Okay, that's the reason you have this half, is because of the 2, okay? So I want to ask you a question. Okay, so we talk about diffusion. We put a lot of time in trying to approximate what is the time particle would diffuse, and I want to raise the question why we care. This is a class about drug delivery, fluid mechanics, particle dynamics. Who cares about diffusion? Okay, so particles diffuse. We cannot get rid of that. It's happening. We can never predict where particle going to be exactly. So we should have some approximation to see what diffusion going to do to us. So let's go here to the board. So for example, let me bring us back. If this is the y-axis and this is the x-axis, and we're talking about the airway. Yeah, this is the airway. Okay, the airway. Okay, and there's some particle. The particle is here at time t equals 0. And in the next time, you know, in a general time, let's do it. General time, and after a while, because of gravity, it's going to go down, right? It's going to go down, and after, you know, a while, because of the flow rate, right, in the lungs, the particle would find himself also in some distance, right? So the new location of the particle is going to be somewhere here, right? You're going to say, haha, the particle got some delta y, and the particle got some delta x, right? This trajectory, okay? What I'm gonna say is, guys, if you're gonna try to do that, that would be wrong, because such a small particles as Brown saw in his laboratory jiggling around and moving. So you need to add here some correction. Because of diffusion in the 1D y-axis, you need to add square 2D multiplied by the time it took together. So if this is t, and this is t plus delta t, so the time you need to put here in your simulation is dt, right? For example, millisecond, okay? And also here, you need to do the same thing, okay? This is the time t plus delta t, okay? So the particle maybe not be here, it's gonna be maybe here, or maybe here, or maybe here. You see the normal distribution? Where's the particle above this axis? The particle in the average gonna be here. But with time, the chances of where the particle gonna be, it's random. Okay? And we need to realize if particle can reach that distance, for example, diameter, or not, okay? In each generation. So that is the idea, but we are facing a major problem. Major problem that I did not show you. We don't know delta square. We don't know tau. And in general, to the television, we don't know what is d. Right? How you can calculate what's going to be the distance. Here we are. What's going to be the distance is the square, right? L diff, because of diffusion and specific time, to dt. If you don't know d, you are screwed, right? So don't worry, you see Albert Einstein here. So in the next, let's take a break of 10 minutes, and then Einstein will help us to realize what is D, and maybe you're going to realize how to get a Nobel Prize for that. Okay, see you soon.